Hello students, welcome to lecture number 16 on our lecture series on classical electrodynamics. And we have seen in the previous lecture, namely lecture number 15, the reason why we have to study the behavior of the electric field at the interface between two dielectric medium. So that is the today's topic will be that we are planning to do how the electric field and the electric displacement vector will be behaving at the interface, that means the junction between two dielectric medium. The reason has been explained in the last class, and if you see the board in the last class, this is the situation that we have in the last class. You just verify what happened in the second result. In our expression, somehow something known as d dot n came into picture, where n is the unit vector perpendicular to the surface. So d dot n therefore represent the normal component of the d vector. D vector means electric displacement vector. So naturally the dot product represent the normal component because n represent unit vector perpendicular to the surface. So it is quite clear that a vector can be decomposed into two components. That is quite familiar thing. Any vector can be decomposed into parallel component and perpendicular component. The perpendicular component is known as the normal component. The parallel component is sometimes also known as tangential component. So parallel and perpendicular is one terminology. Tangential and normal is another terminology. So in the case of the electrodynamics, typically the second version of the terminology is frequently used. That means tangential component and the normal component of the vector. This will be the terminology frequently used in electrodynamics. So you need to know tangent to what, normal to what. That is very important. Whether it is tangent or normal, everything is with reference to the surface of the dielectric. That is important. If you don't tell what is the surface, you also do not know what is the tangent to the surface. So tangent is defined to the surface and normal is defined also to the surface at a particular point. So therefore first you should have a surface, then only we can ask the question what is tangent and what is normal. So where from the surface is coming is when you have a dielectric material, the boundary of the dielectric material will provide the surface for you. And therefore this is the quantity which is going to represent the normal component of the d vector. So there is a reason that since such kind of expression has naturally evolved in yesterday's calculation, okay, in rewriting this quantity, what is known as the normal component of the polarization, electric polarization, okay. So this is how the expression has appeared, and therefore there is a reason that we should know how the electric field and the electric displacement vector will behave at the interface of the two dielectric materials. So in order to study the behavior of the electric field at the interface of the two dielectric material, you consider two dielectric materials. So that is what I am showing, one in the light green color and the other one in a light blue color. So the shape and the structure of the material is immaterial, it doesn't matter. So I am trying to draw some kind of a boundary line, which is this slant line that you have. Okay, so the line that I am drawing like this, okay, and then looking like a total triangle here you have, that will form one dielectric material. Okay, and the shape is not at all important, whether you're going to draw a triangular shape like this or spherical shape. Okay, whatever shape you write doesn't matter completely, but let us have some kind of straight line behavior here so that the integration will be comfortable. We are going to perform some integration corresponding to the curl of the electric field equal to 0. So if you are going to take some kind of a complicated without having a well defined geometry, then performing the integration would be difficult. That is the reason why we have chosen like that. So it doesn't matter whatever be the shape. That is the point that I am trying to explain. So all the green color, the entire region is, let us say that this is a dielectric material. Medium means material. Let us consider that this is a second material and the first material is the one which is in the blue color. You can consider that it could be air also. Even if it is air, we can always consider whether the epsilon r value is 1, that's all fine about. But whatever be the case, it is a dielectric medium or material. So whenever you are going to have one medium in your laboratory, then automatically surrounding that region, there is always air present in the system. So this is one way you can imagine. Or you yourself can have two dielectric medium which are in contact together. So either way, this is a possible scenario. That is the first point that I would like to say. And so therefore the point is that you have a medium 1 and you have a medium 2. What is the major difference between the two material medium is that the electric permittivity, that means in terms of the dielectric constant, we can say that the dielectric constant of the material medium 1 is going to be different from the dielectric constant of the material medium 2. So that is the main reason where you are showing the distinction, or that there is a difference between the two material. So in terms of dielectric constant, it appears. And the interface is going to be looking like this. Okay, any structure is fine. So I'm now keeping like this. The point is that you need to have a normal to the surface and tangent to the surface. As I already explained, we are going to decompose the vector in two directions. One is the parallel and perpendicular component. So the parallel component is what we are going to call by the name tangential component. Tangential means tangent to the surface. So remember that this particular line, yellow color line that is going like this, that is the surface, or we say that the interface between the two dielectric. We can consider that as the surface of the second dielectric medium, right? You have the surface. So parallel to this, what is the electric field? So you can decompose. So this is the parallel, and perpendicular means perpendicular to the surface. So only when you have the surface you can draw the perpendicular. Okay, otherwise you can't draw. So this is how you start with, first of all. And once you have this kind of a setup, now we can assume that there is a uniform electric field in a particular medium. Let us say that we have an electric field in medium 2. And anyway, electric field is not visible, right? So electric field is uniform, that's fine. But since it is not visible, we can now show in a form of arrow or vector. The length and the direction of the vector will tell you how the electric field is. So let me therefore draw a vector showing the appearance of the electric field. So I am writing here E2 in order to say that the electric field is inside the medium 2. If this electric field will not stay here, of course, the electric field means it has to occupy the entire region of space naturally, because the electric field is emanating from the charges. So once the electric field emanates, it will occupy the surrounding space. Okay, whether you have whichever dielectric medium, the electric field will be occupied, excepting for conductor. If you are going to have a solid conductor, only in that region you have zero electric field. But in all other cases, the electric field will be present in the surrounding region. So what is the question that we are asking is, if this is the electric field in the medium 2 that I am going to keep like this, what will be the electric field in the blue color region? If there is no difference between the two medium, okay, if there is no difference between the two medium, how the electric field will look like? It is just a continuation. That means the straight line you just extend. If we extend this particular straight line, it is the same direction. So the direction of the electric field will be the same. The strength will come down, that like 1 over r square anyway, that is only magnitude. So in terms of the direction, it will maintain as the original white color arrow that you have. So that will be the situation when the material medium 1 and the material medium 2 are identically same. If both the medium are identically same, then there is no doubt about that this particular vector will be having the same shape in this particular region also. So now, because the mediums are two different mediums here, what will happen to the electric field vector E2? So anyway, it cannot maintain the same angle, and therefore it has to be taking a different angle. So therefore, in order to visualize how it is, in which direction it will change, that we do not know. So let us assume, or let us simply draw another vector with a different angle. So for this purpose, let me therefore show that there is some angle here, theta 2 for example. Because this is the medium 2, I am writing it as theta 2. And if you are going to assume that the electric field will be in a different direction in the first medium, I will say that this is E1, then you will be having a corresponding angle. So the point is that you should show a different angle. If you are going to show the same angle, which then there is no difference between two dielectrics. Okay, so for that purpose we have to show theta 1 is very different from theta 2. So we do not know whether the point to be noted is that in this particular scenario we do not know whether theta 1 is going to be larger than theta 2. That information right now we do not know. That will come from the value that you are going to substitute for epsilon r1 and epsilon r2. So for now, theta 1 is not equal to theta 2. That's all about. Which is greater, which is lower, right now we do not know. It's only different. That is first thing. And the second thing is we also do not know whether the strength of the field will be identically same. We do not know right now. Okay. So therefore, I am also schematically informing this particular information, namely that the length, if you see the length of the white arrow is different from the length of the yellow color arrow. That means the electric field in the material medium 1. I am trying to say that the angle is also different. I am also saying that the magnitude of the electric field may be different. I am not saying it is different. It may be different. Right now we do not know. Let us finish the calculation and then see how it turns out to be. So this is how you start with. So once you have this information, then we can try to do some calculation based on these angles. So in order to perform some calculation here, you have to be, I would like to explain before moving further. What calculation you are going to use is the fact that for the case of the electrostatic fields, you have the curl of the electric field is 0. So whenever the curl of the electric field is 0, you have an equivalent expression, namely the closed integral of the E dot dl is 0. Both of them are equivalent. So which means that we are going to perform the line integral E dot dl, right? So we need some kind of a closed curve. The closed curve can be in the form of a circle, it can be in the form of a triangle, a rectangular shape, or you can draw a square, whatever it is, or without any kind of shape also you can draw anything you like. Anything is a closed curve. So we need a closed curve so that we can perform the integration around this point where there is a transition from one material to another material. So we can now, here you can see the dotted lines here. I'm trying to select some kind of a rectangular region which is a line integral. It's only a line. Okay, so therefore we are going to perform the integration along the dotted line. That means along the rectangular line that we have. I don't want to call it by the name rectangular box or something like that, because it is not three-dimensional. Okay, it's only a line that we are going to travel. Okay, so we will be traveling like this and then we will be coming back like this. So now what is important is that since we have to give the labels and etc., drawing a very small rectangular region is not easy to visualize because of the the small size. And the point to be noted is that, let me enlarge this, okay, so that it is easy for the calculation. But before that, make a note. What is the point to be noted is that this particular thing, what you call the height of the rectangular region, we can say h. And because we are going to consider only the interface region, interface means this yellow color, you should now consider the limit of h approaching 0 at the end of the calculation. That is a point to be noted. So this is the height, right? This height should tend to 0. We have to make the calculation in such a way that the height of the box is approaching 0. When the height of the box approaches 0, what happens is you are going to concentrate on the interface. Okay, otherwise what will happen is you will be considering the material medium 2 and in this region and material medium 1 in that region. So both of them will enter into picture. So that point should be clear. You consider first of all this region, then at the end of the calculation you have to consider the height of the region approaching 0. The width of this need not approach 0. We can consider some finite value. Let us consider the this particular width. Let us call it by the name length here. So let us say that this is L. So in order to show the geometry or something like that, I would like to enlarge this. Okay, even though we are going to perform the integration in a small rectangular region like that, but for the purpose of illustration and then writing down the geometry, I need a little bit bigger rectangular box so that it is easy to visualize. And then I would like to give some labels. That is the reason. Okay, if it is too small, it is difficult to see. Something like that. Okay, so I think that size is something okay, visible. And that's okay. So once you have this, now we can show some kind of coordinates. So let us consider the Cartesian system in which the origin is this. So this is important. We have to choose an appropriate coordinate system so that you can perform the integration. And let us consider the normal to be the y-axis. Okay, and the x-axis, let it be coinciding with the what I'm trying to show is the interface. The interface, this line, that itself is the x-axis. That's what I'm trying to say. So this will be the origin. If this is the origin, then this will be the x-axis, and that will be the y-axis. So let us choose x and y-axis like this. Then we can perform the calculation. So let the origin be there. So that is what I am trying to say. And once this is clear, then I would like to give some symbols or something label like ABCD. So let us give some labels. This is A, B, and then you have a C, D, E, and F. So F means that point, and similarly C means the point that you are going to consider, because that is a place where you are not changing the material. So once this is clear, then let us consider some length, etc. But how do you write down the vector, or how do you decompose the vector? That let us see. So how do you write the electric field vector E1? So electric field vector can be written like this. You consider the tangential component. Tangential component means what? E1t. I will write it as E1t for the tangential component. Then that is along the x direction. So that will be along the x direction, plus E1n will be along the y direction. So you can easily understand what is the meaning. So you have to travel like this by an amount of E1t. So up to this, that is what is E1t. E1t means from here to here. Then afterwards, you have to travel in the vertical direction like this until you reach there. That is the E1n. So E1n represents this vertical region, and E1t is this horizontal region. Horizontal means, remember, parallel to Ax. Okay. So the moment you say that this is x-axis, we have to always imagine that x-axis is horizontal and the y-axis is the vertical. So you can therefore understand that a vector is now decomposed into the parallel and the perpendicular components at the interface. That is what it is. And this is what is the parallel component, and this is the perpendicular component. And the same thing can be done even for the second one. So let me write down for the expression for the E2. So E2 tangential component x-axis, and similarly the y-axis component will be E2n. So n means normal. That's all about it. And therefore, for visibility, I will always show that what do you mean by E2t. E2t means tangential to the interface. This is the interface, right? So this is interface means this is also parallel. So that parallel is known as the parallel component. I think that color, this pink color, is not good. Yeah, so since the pink color was not good, I just changed it to this so that it is visible. So now you understand what is the meaning of E1t, E2t. So exactly what you are trying to say is that the white color vector is now decomposed into a component that is parallel to the interface, that is this line, that is the x-axis, and then after making the decomposition in this direction, then you'll have to travel in the vertically up direction, and this value, that is a numerical value of this height, is what is E2n. Therefore you can easily understand what is the meaning of the E2t ax plus E2n ay. So that sum will give you the electric field vector E2. So similarly, this is the meaning. So once this is clear to you, you can now proceed, and then let us go back to the board and then write down this expression. We are going to write down this there. That is first thing. Second thing is, you should remember that the x-axis and the y-axis are not the usual horizontal, but we are now you are now considering the x-axis to be aligned with the interface between the two of them. So that should be clear to you, and that is the second important point to be noted. Third point to be noted is that the angles are always measured from the normal. So the normal means normal to the interface, and we are choosing that itself as the y-axis. Now the angles are always measured from the normal. Okay, otherwise it will be some confusion. This is the standard procedure, and therefore that's why this angle is present here. For the theta 1, you can see that we have to draw like this, and then arrow is here. And whereas for the case of the theta 2, you start from here and then you end here. So the arrow is there at the other end. So that means the measurement starting point is the normal. This is the normal, and then from there you start your measurement. That is how theta 1 and theta 2 are measured usually. And therefore once these things are clear, and then you should always remember means keep this kind of diagram either in a sheet of paper with you. Otherwise, writing down the equation based on this diagram will be, and every time you have to come back to this diagram and then go back to the board. Okay, back and forth you have to scan. Otherwise it will be difficult. If you have written all these things in your notebook, for example, then you can always verify that we are going to perform the integration from A to B. You're going to perform an integration along this path, then from B to C, then C to D, then again come like this in this direction, which means D to E, and then E to F, and F to A. So if you perform the integration like that, we will come back to the original place. That means our starting point is A, which means that your integration is from A and the ending point is also A. Since the starting point and ending point are same, the integral will give you 0. And since the integration is performed along the line, this integration is known as the line integral. So essentially we are performing the electric field E dot vector, the dl means the elemental distance. If you move, this is another point you should remember, that when you are traveling like this in this particular direction, what is the direction means ax will be the direction. That is a unit vector corresponding to this movement. And once you finish coming up to the point B, you are going to travel like this along the BC. When you are traveling like this, what is the vector for you means vector will be opposite of AY. See, that is important. AY is pointing in this direction, right? When you are traveling in the BC and then CD, okay, when you are traveling like this, what is the direction means minus of the AY. AY is this. So that is important. We are going to substitute this kind of thing in our integration. Therefore you should remember what we are going to do with this diagram. Okay, and if you are going to have, or if you have already written it on your note, then it will be easy that you can always see the diagram and then write down the equation. And once you finish coming to the point D, you will be traveling in this direction. So when you are traveling in this direction, what is the vector means it is the negative of the AX. AX is this direction, right? So negative. Why do you want to have this direction means origin is here. See, if this is the origin, then that should be the increasing direction. If this is the origin means that is it. So these two directions are clear. So based on that only, now we decide that when we travel like this and then reach the point A, our unit vector will be negative of the AX, negative of the AX unit vector. And similarly, when you travel from E to F and then again from F to A, our unit vector will be plus AY. It is the same thing as this. So these are the things that you'll have to remember, or you'll have to register in your memory, that we are going to do the calculation. That is first point. And second point is that you can consider the height of the rectangle to be h, total height. Total height means B to D will be h. If it is the case, B to C will be h by 2. C to D will be h by 2. So we can always consider half of the height for this. That is one thing to be noted down. And then the length of the rectangle from here to here, we can consider something like capital L. You can consider whatever it is, but let us have these kind of numbers, and then it will be easy to perform the integration. So let us therefore go to the board. We'll move to the board and then write down the expression for the E1 vector, that is this expression, and then the E2 expression. And after writing that, I would like to evaluate the line integral. Okay, so let me go to the board now. So I am simply writing down the expressions for the E1t and then the E2t. And as I already explained, I would like to just mention what is the small element. Whatever element that you are going to consider, we can call it by the name dx. Okay, so anyway, the integration is so simple that the integral of the dx is the total length. But for formally to write down, I am saying that a small element will be dx, and similarly for y direction I don't want to write. You can imagine that dy will be the small element, and therefore we would like to say that AB equal to L, that is the length there, and correspondingly the height let us consider to be h. Okay, so let us again go back to the board and then write down that we are going to consider the static electric field. Okay, so for the static electric field, what do you know? We know that the curl of the electric field is 0. So which is equivalent to this integral. So I would like to explain again. Of course, it's already explained. I would like to say that what is the loop that we are going to consider. So you know what is the loop. It is going to look like starting point will be A, travel along A, B, C, D, E, F, and then come back to the A. So as it is shown in the diagram. So once again, this diagram is quite clear. And then we are coming to A to A, and then keep these values L and H. That's all about it. And therefore, let us evaluate the integral. So the closed integral will be given by, okay, so the closed integral is given by the sum of the several integrals, small integrals. So simply you are going to write down along each path AB, then BC, etc. Okay, once you go AB, the next one should be BC, right? That's correct. Then every time you simply write down E dot DL, and then we can do the simplification later, and keep doing this until you reach the until you finish all the small parts of the expression. Okay, so all that equal to coming back to 0 means, yeah, that is same. So that is explained why it should be 0. You are coming back to the original place, EF, and then FA is correct. E dot dl. Once you come back to the original place, 0 is the total integral. So if I can write down one expression, I mean one of the integral, then the rest of the thing is quite simple. There is no difficulty in evaluation. So let me write down the first integral in a bracket. So if I write in a bracket, you can easily understand. So now how we are going to write down this expression is this. The electric field vector, now what we are going to consider is electric field vector along AB. That's what you have to see. So how you understand like this is the following. Okay. AB, what is AB path you should know from the diagram. That is one thing. Okay. So AB path is a path which is parallel to the x-axis, right? Therefore, what is the electric field along that path? Electric field along the path AB is equal to E1t in that direction. That's all. There won't be any normal component along the x-axis. That is what I mean to say. So the electric field will be naturally only that component will be valid. If you are going to consider the perpendicular component, you can always consider, but the dot product with the DL will go to 0. That is what I am trying to say. So if I write down the dot product, you will be understanding what it is. So the DL, let me therefore complete this unit vector AX and then close this, and that's all about it. And you see the integration is already completed. The integral is already over. What do you mean by integral is over is the integral of the DL is the total length. So that total length is written here. That is why the integral is simple. And then the total length, whether it is positive of the AX unit vector or negative of the AX unit vector. So that will come from the path AB, whether you are traveling in the direction A to B or are you going to travel from B to A. So that information is here available. Now since it is traveling from A to B, the unit vector is a positive unit vector. Similarly, for the electric field, if we have already written down what is the vector, so that will not change now. Okay, if at all the unit vector is changing, it will change when you are traveling along a particular length. Okay, electric field will not be affected because of because of your walking. So therefore, this will always have the corresponding ax and ay. Now, since we are going to put a dot product here, so ax dot ax will become 1, which means that the tangential component will survive. So in case if you are going to write down the full expression, what I am trying to say is, in case if you are going to write down the full expression for the electric field, namely E1Tax plus E1Nay, normal component also if you write, nothing wrong, you can write down. But what happens is the Ay you have, right, the normal component, if you take the dot product, then that will become 0. So the y component of the electric field, even if you write that component goes to 0, so there is no need to write. That is what I mean to say. So once this is clear to you, you can therefore write down the rest of the integrals. So in this integration, what you have to do is that you are going to travel from B to C. So B to C means which direction? That's what you have to remember. B to C means you are going to travel from up to down. Up to down means negative of the y direction. So that unit vector you have to appropriately substitute. That is first thing. Second thing is, which component of the electric field will survive when you are traveling in the vertical direction? Vertical direction means along the y-axis. That is the meaning. Okay. So and you should remember, in our diagram y-axis. Okay. Don't take a general situation. In our diagram, what is the y-axis? That y-axis is the one that you have to remember. So the electric field will be the normal component will be surviving. So if these things are staying in your mind, then quickly you can then write down that only the normal component E1n ay, then dot, the height is now h by 2, right, and therefore minus of the ay. So this is clear. And similarly, once this is clear, you can once again write down what will be the corresponding expression for the CD. The expressions are very similar. Only thing is you have to be careful whether it is plus ay or minus ay, and that's all about it. And therefore, let us complete the remaining expressions, the each integration. L into minus ax, so that is the over, then plus you have E2n, then you have the ay cap, then you have half of the height, then positive of the y direction, and then you have the last term. So the last term will be in the first region, therefore I will say E1n in the positive y direction dot half of the height is there, and then along the y direction, all that equal to 0. So that's all about it. And now that the integration is completed, I mean simplification of the integration is also now easy. In what way it is easy is that some of the terms will cancel. So let us therefore identify which terms are cancelling. This is not difficult. You can see that some terms are cancelling. Okay, so the white color highlight, I will search it. See the another term which is there, right? The another white color highlight. These two terms will cancel. You can easily see. You can easily see that this one and that one are identically same, excepting for a minus here and plus here. Therefore, this will completely cancel with this term. And similarly, you can discover another term which will cancel. See here you see E2n, ay, h by 2, h by 2. So there is a minus, there is a plus. Therefore, these two terms will again cancel each other. So I would like to highlight in another color, maybe in green color. So this will cancel with another green color term. And that's all about it. And you see that you have 1, 2, 3, 4, 5, 6. So out of the 6 terms, 4 of them will be cancelling and going to 0. So we are therefore left out with only 2 terms. Only 2 terms. And then ax dot ax will give you a scalar 1 only. Okay. So therefore the integration is now become quite simple. And finally, what is the conclusion is that if you take L common, I think that L is a common there. So I'll write down L. If you take common, there is no dot product now. Okay, no more vector now. So E1t minus E2t is equal to, okay, that is equal to 0, we can say. And here is the point that this is not the dot product. Okay, because dot product has disappeared. Okay, a dot ax will give you 1. So all are simple scalar products, and therefore this small dot that I have kept is only a scalar multiplication. And you have a product of 2 terms are going to 0, which means that either you say that L equal to 0 or you say that the quantity inside the bracket is 0. But you already know that in the rectangular region that we considered, we are not going to consider L equal to 0. That option is not there. If at all, if you want to make something approaching 0, as I already explained, we have to consider H approaching 0. the height of the rectangle should be approaching 0. So in the limit of the height approaching 0 only we are interested in. That is how we have to do. But interestingly, what happened is in this expression, already those terms containing the height is already naturally cancelled. Therefore, we don't have an additional work for taking the limit of h going to 0. You can't do it because it's already cancelled. No, h itself is not there, so there is no need for you to worry about limiting the limit of the h tending to 0. Such calculation is now not required, and therefore we can write down the conclusion now. So since L is not equal to 0, we are going to make a conclusion that E1t is equal to E2t. So this is a very important result, the first main result that we are going to get, and therefore I'll say that this is the result number 1. This is quite important. Boundary condition on the tangential. How do I read it, or how do you understand it? Let me explain the meaning. Therefore, the meaning is that the tangential component of the electric field, the tangential component of the electric field vector, I'll say E vector, is continuous. The continuous is the English word corresponding to equality. Is continuous across the boundary. Either you can say interface, across the interface, or boundary. We can say interface or boundary, whatever it is, across the boundary of the two dielectric medium. Of the two dielectric medium. So this result is quite important, and therefore you should know about this clearly. We need it. We need this information in order to solve some of the problems. Now the statement. Let us see the statement. T. This T is the tangential component. That means parallel component. Parallel to what means? Parallel to the interface. And where from interface came? Interface came because you are going to join the two dielectric medium. When you join the two dielectric medium, I get that interface. Parallel to that interface is known as the parallel component. Parallel component is known as tangential component. That's what it is. So both of them are scalar here. Now what do you want to say that equality? There is equal, right? The equal is what is written as continuous. Actually, you should say that the tangential components are going to be equal, but the different style of writing the sentence is to say that it is continuous. Usually continuous means when you are going to plot a graph, when you have the same value, what happens is the curve is continuous. That's what it is. In terms of graph, you can see if you already have a curve, and then if you have a different point suddenly, then there will be a gap between the curve. Then we say it is discontinuous. So when you have equal value here, what happens is that if you are going to plot a graph, then the curve will be a continuous curve. For that reason, we say that the tangential components are continuous. Continuous is, remember, this expression is valid only across the boundary. When you are crossing the boundary only, this is valid. Once you have put your step and crossed the boundary, there is no such equation. That's all. This equation is no longer coming into picture. So this equation will come only when you are crossing the boundary. Okay, only one step. One step is before boundary. Your next step should be after the boundary. So one step, if you put, you cross the boundary. At that time, this expression will come into picture. And once you crossed it, and that's it, there is no use of this equation. So that is a point to be noted, and therefore our conclusion is that electric field being a vector quantity, this is a vector quantity, we have made a conclusion about only one component. This is vector. Vector has two components, right? In the case of the planar region, we have only two components, only the tangential and another is normal component. So we have therefore completed, or somehow it came like this. Okay, when you are performing the calculation, it so happened that we got the conclusion about the tangential component. But we have to now ask the question, what about the normal component? Naturally, that question is there, and that has to be done. But before that, let me make that particular point, that what will happen to the normal component. Keep that question, and then after that we will move ahead to the how to deal with the D vector. It's in white color I'll take. So immediate question that you can ask is what is your conclusion about the normal component? That is a natural question, but right now we do not have the answer. Okay, we have to come back to this point later. But before discussing on the conclusion about the normal component, I don't want to discuss about the normal component right now. But instead of that, I would like to first of all finish. I would like to first of all finish the once again gone there. It's gone somewhere. 1 second. Yeah. So before discussing the normal component of the electric field, there is one work is pending. What it is what will happen if you multiply this quantity by epsilon 0 into epsilon r? You know that epsilon multiplied by the electric field will give you the electric displacement vector. So therefore, if I multiply by the corresponding epsilon r, okay, with epsilon naught here, then I will be able to get the relation for the electric displacement vector also. So it would be nice to finish the electric displacement vector d, okay, electric displacement vector d before going to the normal component of the E vector. That is a plan now. So let me move to a different place in the screen and then explain what will happen if we multiply this by epsilon 0 and epsilon r. So here I have written whatever I explained. So let us therefore discuss about the d vector once we have the relation for the tangential component, and the idea is that we are going to use the d equal to epsilon into E, and the information about the E here has to be transferred here. That's what we are going to do now, and for that purpose, okay, let us have the appropriate symbols. As you know that let us represent d1. So what should be the d1 then? D1 will be the electric displacement vector in the dielectric medium 1. Okay, so these are the naturally one can understand that it is in the medium 1, and similarly you can write down what will be the displacement vector in the second medium. We can represent it by d2, and the corresponding components, how do you write d1t? So d1t you can easily understand that it will represent the scalar quantity, namely the tangential component of the d vector in the medium 1. So the terminology is quite simple, and similarly d1n can be used for the normal component. So once these things are clear, we can now write down the equation. So d equal to epsilon r, right? So d1 equal to epsilon 0, then epsilon r, then we say electric field in the first medium. So once that is clear, now let us decompose into parallel and perpendicular component. That means I will write down like this: d1t in the x direction, followed by a normal component d1 n into y direction. In the same thing, you repeat it for the case of electric field, which we have drawn in the diagram. In the diagram itself, I have shown this same thing. So if you compare component by component, both side, that means compare the x component, compare the y component, I will be able to get the two equations. So, and not only that, similarly d1n can be written down as e1n, etc. And so you are able to understand how this expression is written, that by comparing the x component and y component, you see here, this is a vector relation, right? So there is an equality here. This equality is there is a vector here. Therefore, this is a vector equality. So vector equality will be valid if each one of their components are equal. That means x component of this and x component of that, those two things should be equal. So that means your d1t, that is what here, d1t should be equal to, then x component is given by epsilon 0 epsilon r into e1t. That's what is written here. And not only that, that is why I have written and. That and means that there is a plus here. So the vector equation is now decomposed into two scalar equation. That is what is this. And therefore you compare the y component. So this is y component. You compare with the y component on the right hand side, we will be getting this equation. And since you have the suffix 1, suffix 1, suffix 1, this equation is valid, or this equation is suitable for material medium 1. And of course, you can always write down a similar set of equation for the material medium 2. So no need to write, okay, all the 1 you have to replace by 2. That's all about it. And so it's quite simple. So I don't want to write the entire equation. Only thing is that we can write d2t, d2n, etc. That's all. And similarly, correspondingly, you should have the epsilon r also 1 and 2. That is important. When you are considering the material medium 1, we have epsilon r1. When you have material medium 2, you have epsilon r 2. So if these things are clear, now we will use the first result that we got. So what is the first result? You remember? I said that tangential components are equal, so that is the relation. So E1t equal to E2t, that is what I mean to say. So therefore I will write down that E1t will be equal to E2t, and together with, not only that, the result 1 has to be used together with, just now we have decomposed, no, that equation number A. So let us combine them. Combine them in, just we are going to substitute epsilon or 1. So where is the 1 there? So you must have the 1. See, material medium 1 should have the epsilon or 1, right? So 1 is missing there. So let me put 1 there. So everything is for the material medium 1, epsilon or 1. Okay, so epsilon or 1. And similarly for medium 2 you can write down. Okay, so therefore right side, so all these things are clear. Now coming to the second right hand side, you can write down epsilon 0, epsilon or 2. And that's all. So almost there, we got the answer, and we can rearrange this in a different style, saying that d1t divided by d2t, epsilon naught cancels, right? Then what is left out? Epsilon r1 by epsilon r2. So this is an interesting result. So this is the second important result that we are going to get on the boundary condition. So I'll put a box or highlight this, and we will call this by the result 2, which is once again important. All the boundary condition relations are quite important, because always you will get some numerical problem for the solution. And once you have this, we can now write down the conclusion. So what is the conclusion about the boundary condition on the electric field? So we can have the conclusion in for example in case A and case B, because there is one situation where equality is there. So I will say that what happens when condition A is satisfied and condition B is satisfied. Okay, so condition A is the standard one, where you have epsilon r1 is not equal to epsilon r2. So you can ask the question, what are we doing actually here? Why, from where the A and B is coming? Now you see that epsilon r1, epsilon r2, what is the meaning? The meaning is, this is the dielectric constant of the material 1. This is the dielectric constant of the material 2. And if you see the reference book, you take any handbook of materials, for example, and then you will be having hundreds of materials. And along with the material, you will also find the value for the dielectric constant. Okay, 100 materials are there, means there will be 100 dielectric constant value, respective values will be there. So there is a possibility that you can try to search two materials such that their values are almost equal. Suppose if the epsilon r1 is equal to epsilon r2, what will happen? That's what I am trying to say. So there is a chance that you can choose two materials in such a way that these two values are almost equal. If it is almost equal, what happens is, this is 1. If these two both are equal, means it becomes 1. If it becomes 1, what is the conclusion? The conclusion is that d1t is equal to d2t. That is what it means. So the conclusion is totally different in this case. That is why we have to be careful. So we have to distinguish between the case where epsilon r1 and epsilon r2 are very different. Very different means, if this is 1 and that is 10. If it is 1 and 10 means, there is no way that these are approximate, and therefore they are very different. In that case, d1t is not equal to d2t. So that is the important conclusion I would like to say, that their tangential components are not at all equal. But consider the opposite situation. Opposite situation means there are many cases where the two of the dielectric material will have almost the same number, like 4.5 for example here, and 4.4 for this. 4.5, 4.4. Practically speaking, mathematically they may not be equal, but practically speaking, this number approaches 1 if the ratio. So therefore, what happens is, we can say that d1t will be approximately equal to d2t. So therefore, there is a possibility when you are going to choose such kind of materials, we have a small option, okay, where epsilon r1 can be equal to epsilon r2. So in such a situation, d1t equal to d2t. So why we are so much worried about whether it is equal or whether it is not equal is because in terms of sentence, when you are writing English sentence, right, it will be totally different. How do you say this? How do you say this? The tangential component of the d vector is continuous. Continuous means equal. How do you read here? Here you have to read in a different style. the tangential component of the D vector is discontinuous. So this is discontinuous and this is continuous. So both of them are D vector. This is also D vector, this is also D vector. So what happens is, as if there is contradiction is there, right? That's why you have to be clear about the if condition. Okay, so this is the most general one. So here this is special case. Okay, this is only when you are going to search the two material in such a way that they have a similar dielectric constant, approximate value. Okay, only then this will happen. Otherwise, usually when nothing is specified about the special case, when nothing is specified, usually we have to assume that material 1 and material 2 have two different dielectric constant, in which case the discontinuity rule is applicable. So this is the important one. Therefore, I would like to write down these statements that I made here. The meaning of the statement is that the tangential components of the D vector are continuous because of the equality, and that is the conclusion B. Conclusion A also you can write down in a similar manner. So, but the point is that it is valid only under the special case. So you should not imagine for all the time. Only under the special case only this is valid. So therefore, make a note that it is not valid in general. So I'll put an important highlight there. And coming to the case A, I mean the first conclusion, what is the meaning? The meaning is that, once again, similar statement you write down, that the tangential components of the D vector, okay, the tangential component of the D vector, we can say that I can say is, right? I won't write is here. So it is continuous across the boundary, sorry, discontinuous across the boundary. Yeah, is it clear? Because of the not equal to sign here, you have to write discontinuous across the boundary. So the one that I am writing in the yellow color is the most general rule that is valid for the D vector, but there are some special case where equality happens. The green color conclusion will come into picture. So I would like to write explicitly like this, because in the competitive examination they may give some numerical value with the two different materials. Then generally you think that D vector means discontinuous. Remember, D vector means discontinuous. That is the general rule. But in order to twist the story, what happens if these two are equal means D vector will be continuous. Okay, so it is easy to remember. D means discontinuous. D means discontinuous. That is the standard rule. Special case means D means continuous. That's all. So that is the main conclusion that I would like to say in this regard. Okay, so the discontinuous and the continuous, two options A and B is there only for the D vector, only for the D vector. So in order to make this comparison, I would like to go and then show the first result. In the first result, there is no confusion at all. So in order to show that, let us go above in the board. So here you have the result now. So here the tangential component of the electric field is only continuous. So there is no other option for you. So that is interesting, and therefore the in a way I can say that the result is always valid. You don't have option A or option B. So there is no such if condition there. That was there in the case of the D vector. Okay, only in the case of the D vector you have no case A, case B. But here in the case of the E vector, electric field vector, it is always continuous. So because there is nothing to manipulate here, and therefore it is always continuous across the interface. So this is an important conclusion. So these results are quite important, because almost every time you will be getting numerical problems to solve boundary values at the interface. So there is a point to be noted. This should not be confused with the boundary value problem that we have been discussing, what is known as the electrostatic boundary value problem. That is different. This is not a boundary value problem. This is the information about the electric field and displacement vector at the interface, or that the boundary of the material. That's all about it. Boundary value problem means it's a differential equation. It's a standard terminology. Boundary value problem means solution to differential equation. This is not, whatever we are discussing now, this is not at all boundary value problem. What is this that we are discussing is, this is the behavior of the electric field at the boundary. That's all. Okay, there is no differential equation. So everything is algebraic equation that you have, and we are saying, or we are calculating whether the tangential component will be equal or not equal. That's all about it. It is as simple as that. So if you are going to write in English sentence, you will be writing continuous and discontinuous. Okay, so keep this point, and then probably in the next class we will discuss about the normal component of the electric field. So today's discussion is all about the tangential component. Okay, normal component we will discuss in the next class.